Okay, let's start. Today I'm going to talk to you about two of the key aspects that have been popular, or at least have been vital to the surging popularity of service computing as it is right now. And basically, the first one of these aspects is the performance model. So, as you might know, with service applications, the idea is that the cloud provider manages basically everything for you. So, what it especially does is do the autoscaling for you, and you can rely as a user, you can rely on their almost infinite amount of resources. Not only that, you can also rely on your service being reasonably available. Just like basically you can rely on it to be available just like any other service, on any other cloud service. And nowadays we all see more and more that people are expecting low latency from their service applications, to the point that you can already see that you can already read some blogs where people are trying out service applications as backends to their web applications or other user-facing tasks. And the other aspect is the cost model. So maybe the most popular thing about service computing right now is that you only pay for what you actually use. You don't pay for idle resources or reserved resources. Not only that, you don't pay for any upfront costs or any recurring operational costs periodically. And even if you do use and pay for your functions, you pay that at a very granular level. So you pay by the millisecond instead of by the hour or day with traditional cloud models. And this might seem a bit counterintuitive, maybe even conflicting, because you don't really think of a high-performance application as also being a cost-effective one. And serverless computing doesn't either suddenly give you magically tons of resources for free. But what it does do is it tries to maximize the performance it can get out of a small amount of resources or a fixed amount of costs. And in this talk, I'm going to show you basically what techniques they use in their platforms to optimize this trade-off between performance and cost. But first, before I actually dive into these optimizations, I would like to give you a short introduction of what a function as a service platform actually looks like. So there's two limits to this talk. I'm not going to talk to anything about other than function as a service within service computing, so not about serverless containers. And I'm only going to focus on the runtime of a function as a service platform. So I'm not going to focus on the developer workflow or how you create or monitor your functions. So to start off with the data, basically the data model of a function service platform, you basically have two conceptual stores of data. So you have, on one hand, you have the function metadata store, where you store all the versioning and configuration related to your function. And the reason why this is there is because of, the metadata is a pretty small amount of data, and and it's accessed frequently and expected to be low latency because it's used for lookups, queries, and so on. On the other hand, you have the function store, where you actually store the actual functions that you're using. So, for example, you can have small Python functions, but this can also quickly go very large, where your functions have many dependencies and many static assets. So then you can imagine that your functions start to become almost tens or hundreds of MBs. And how we actually can execute these functions is basically using a couple of components which comprise the runtime. So here you can see we have a router which basically is responsible for getting in the requests for function executions. We have a deployer which is responsible for actually deciding how a function will be executed. And basically for most platforms, the deployer actually hands off the actual deployment of the resource to a resource manager. And since we're here at KubeCon, this of course is Kubernetes. And in the end, what they are is a function instance. So, and that function instance is basically a worker which can accept requests and execute the function and respond. And to give you a bit of a concrete example, I'm working on a platform called Fission. And if you strip out all the more complex components and optimizations, you see the same model in our platform. Because we have a router, we have a thing called an executor, which is similar to a deployer. We use custom resource definitions as our function metadata store, and we have a small function store by default. And also this model gives me the opportunity to also to address the elephant in the room, which is the cold start. And the cold start is basically the worst case behavior of your functions. So it basically you have no caching involved or no shortcuts you can take for executing your function. So how this looks like is, to give you a small, basically a bit of a visual example, a request comes into the router checks and has no function instance available, so it will query the deployer to actually deploy a function. The deployer will fetch the data from the function metadata store to decide how to actually deploy this function. Well, this decision is then handed off to Kubernetes, and Kubernetes does the actual deployment of the function instance. And only after all that, then you can actually forward the request from the router to the function instance. The function instance can execute the request and respond, and the router can forward the response back to whoever is waiting for it. And now contrast this with the best case. I don't think it really has a name, but I'm just going to call it a warm execution. And here, of course, the function instance is already available. So that's really ideal, because then you can simply forward the request immediately to the function instance and get back the response to the user or service that's waiting. So maybe it is better to actually look from a performance perspective on what actually involves between these two cases. So at the top we have a couple of, for the cold start we have a couple of service requests. Then we actually have to fetch the function metadata from a store, so etcd. I'm not quite sure, but I think it's about tens of milliseconds in the best case. Then you have to deploy you have to wait for Kubernetes to deploy your resources, which, well, as we know, we count in seconds. And then we actually have to transfer the function to the resources, which can, if your function is larger, it takes also a couple of seconds. And then we still deploy the function, also takes some time. And only after that we can actually forward the request and execute the function. Warm execution, you only have the two last steps. You just forward the request and execute the function. And it's not just our Kubernetes-based model. This is true for any platform. So this is recent research published last summer, where they evaluated the cold starts of the big three cloud providers. And even there you see that even in the best case, so for the most production-ready service platform, which you can say is AWS, there's still 200 millisecond cold start delay. And that's pretty significant, especially for performance-sensitive applications, where your cold start is 200 milliseconds and your warm start is a couple of milliseconds of overhead. But still, this is very impressive, because it's very hard to actually get to this kind of performance with a large-scale service platform. And so, as I mentioned before, in the rest of the talk, I'm going to show you some of the techniques that are actually using to improve the performance. And also, basically, at what cost? Because it's easy to simply throw more resources at your problem and get it faster, but it's more challenging to actually think about how can you get more performance for the same amount of cost. So the first optimization is what we call function resource reusing, and the idea is basically to reduce the number of cold starts you do. And the idea behind this is a bit of a theoretical one, because at the most theoretical point of view, you don't want your function executions to be able to influence each other at all. So in basically the most extreme case, you want to have a function instance per function execution. So that also means that every function execution will have a cold start. And of course, you can try to avoid this by trying to share function instances between function executions to be able to share these resources between the two. And that's not to say that the leftmost example is always a bit silly. Because there are many reasons why you actually want to have this performance isolation. For example, if you have very security-sensitive functions where you don't want executions to influence each other or eavesdrop on each other. But in practice, we see that all function service platforms actually use some form of resource reusing. So for example, all your functions, when you start functions on AWS, these are typically grouped on the same machine. So your function already reusing the same hardware resources. Still, these functions are not shared themselves because they are still virtualized or containerized, basically pretty well isolated from each other. But the function executions, these are actually sharing the same function instances. So it's certainly, the reusing is certainly used in practice. And just to update our model a bit, we can reflect this optimization by adding a cache to the router. So whenever a request comes into the router now, we first check the cache if there's an active function instance, and if so, we forward it to the function instance. If not, we have to go through the entire cold start. But of course, this also involves a trade-off, because how long do you keep your function instances alive? You can keep them alive for a very long time, ensuring that that any subsequent execution will be able to reuse these function instances. However, of course, that doesn't mean that you guarantee that actually will be useful. So it might be that you're just keeping around idle resources for a long time. So the opposite, of course, is then to keep it alive very shortly, reducing your cost of idle resources, but less functions will be able to reuse existing function instances. So not only can you share the resources between and after your function instances are running, you can also try to share them before the deployment or during the deployment. And basically the insight here is basically that the function instance as a component exists out of two parts. One part is the function-specific code, which is basically the code that you as a user provide. Basically, it's all your business logic. And the other part is the runtime. So that's basically all the operational logic that's necessary to actually make this function instance executable, monitorable, and so forth. And with this insight, you can actually divide the deployment process into two stages. So you can first deploy the runtime, creating a generic runtime. And only then in the second part of the process, you actually deploy the function on this generic function runtime, creating the actual function instance. And then that allows you to do something that's that's very common in many domains, which is called resource pooling. So you might, for example, know in multi-threaded applications, you have these thread pools which you use to try to avoid this costly operation of creating and deleting threads. And serverless, this works very similar. So what you can do is keep a pool of, so for example, 3 function runtimes. And when you need two functions, you will take 2 generic runtimes and only do the last step of this deployment process to actually create these function instances. And only after that, you can start to rebalance your pool asynchronously. And we can, of course, again extend our model with this optimization by reflecting this distinction between the runtime and the function instance. And we have the additional component which we call the resource pool, which is responsible for keeping or maintaining this pool of generic runtimes. And also this has a trade-off, of course, because how big do we keep this pool? We can go for a very large pool, basically meaning that we, regardless of how many workloads we get, we always have enough of these generic runtimes in this pool to actually give to these functions to be deployed, increasing their speed. But of course, especially if you're not actually needing so many, if your workload is not that high, then you're still incurring all these constant costs of having to maintain this pool at all times. So the opposite approach would be to actually create a smaller pool, even no pool, where you ensure that you have very few resources used. But the problem, of course, here is that even if you have a very small spike in your workload, that already you exhaust your pool, and all the subsequent functions will require the entire cold start process, where you have to also deploy the function runtime. And so not only can we prepare this runtime part of the deployment process ahead of time, we can also start to prepare more of the function part of the deployment process. And we can do this with a optimization called prefetching. And the idea of this prefetching optimization is that you fetch basically you proactively place your function sources near the runtimes that actually need them. And this might not actually make sense to you if you have a small cluster with a few nodes or with a few functions. But once you start to get into a more larger scale operation with many functions, with functions that are far larger, that are tens or hundreds of MBs, then suddenly this cost of having to transfer your function data, your function sources to this runtime can take quite some time. So especially for use cases where we in the geo-distributed world and in the edge computing world, you can see this as being very important. So I'm fairly sure that AWS Lambda at the edge and Cloudflare are using some form of prefetching. And you can think about this prefetching as being a hierarchy of layers. So at the top you see the remote storage, where you actually store where your function is actually stored, and below that you have several layers of possibilities to cache your functions before they actually are used. So for example, you can cache them at the cluster level, or at the most extreme, you can cache them at even a runtime level that you already place them at the runtimes in those resource pools ahead of time. And this, of course, again, is a trade-off, because you can, if you go for the most extreme way of basically caching your functions everywhere, you're pretty sure that your performance of basically your cost of transferring this function to the runtime is very minimal. But of course, you are incurring a lot of storage costs, and so incurring a lot of storage costs because you're caching everything everywhere. And of course, the opposite is also, again, the opposite of the trade-off, where you save on the caching costs, but you pay for it with a higher latency in some cases. So just to keep up with the pattern here, we can now add this optimization also to our model, and the cache is then added in front of the function store, just to indicate that we don't necessarily need to fetch this function that we need from the function store itself, but we can use an intermediate cache. So that brings us to the last optimization, which is function prewarming. And the idea of this is very interesting, which is basically that you try to anticipate function executions ahead of time by deploying these functions predictively, which we call prewarming. And it sounds fancy, but this optimization is not new at all. You might know it from other domains, such as the branch predictor in the CPU or proactive autoscaling. But maybe this is more easily explained with a visual. So here you can see in the red is the amount of function instances that you need at one point, and in blue the amount of function instances that you deployed. And in a situation where you have no prewarming, at some point your platform will recognize that it needs a function instance, and only then you can start to deploy things. And that's regardless of how much you optimize your cold start process, you will always, all of this cold start latency that you actually have will be transferred to the user. And compare this with an ideal case of prewarming, where you know exactly at T4 that there will be a function instance needed, and you can just deploy it just ahead of time, ensuring that the user will not notice any cold start. But as you can imagine, predicting things, and especially function instances, especially function execution, is hard. It's also an active field of research in many of these related domains. So for example, proactive autoscaling is still a trendy subject for researchers. But there are approaches to solve this problem. It's basically there are two types. One is runtime analysis, where there's a component constantly analyzing your function and its behavior, and tries to, based on like some mechanism from simple rule-based to complex machine learning approaches, to create a model to predict the future function executions. The other approach is basically to use more of static information. So use the information that the function as service platform actually has to his benefit. So if you, for example, already know that function B will be executed after function A, you can already start prewarming. Or if your user already has set up a trigger to execute your function every day, then you know when the function will be needed. And of course, it also, again, involves a trade-off, because a prediction is never certainty. So you have to decide on when you start to believe that a prediction will actually result in a prewarm. So for example, can you keep the threshold for believing these predictions very low, meaning that even if there's a slightest hint that there might be a function execution incoming, that you already start prewarming your functions. And of course, this also leads to a misprediction probability, where you waste a lot of resources on function instances that are not where the function execution didn't actually arrive as predicted. And maybe just a small example here. One of the oldest tricks in the book is basically what I'm not sure if there's a name for it, but I'm calling it ping hack. Is where people, when AWS just started, they set up a timer and then basically triggered their functions every 5 minutes, just to keep it warm. And this is of course very simplistic and only works for one function instance, but it's already a most extreme form of optimistic prewarming. And on the other side, you can be very pessimistic, of course. You can say, I'm keeping this threshold very high for believing a prediction for a function execution. And of course, now the downside is the other way around, because now you save resources on mispredicted prewarms, but you also have more function executions that cannot benefit from this prewarming because they just weren't predicted certainly enough. And to give you an example of this pessimistic prewarming, I just want to introduce a project I'm working on right now, which is called Fission Workflows. And Fission Workflows is an approach to basically to compose functions together into more complex function compositions. So this allows users to basically reuse their functions instead of writing them from scratch, or instead of having to write all this low-level data transfer logic themselves, to use this system to create these function compositions, which we call workflows. And not only that, it also gives you additional features, with basically provides you monitoring, provides you persistence of your data, and some other fault-tolerant mechanisms. So just to give a small example, here's a small gopher that gets into a workflow where we first validate it, then we branch it off into a parallel execution, where in one branch we actually resize the image, in the other branch we actually start to do a sequential execution, where we first do an image recognition, generating some tag, and the tag we translate, and then we have a final function where we combine these two branches into a resized image with a caption. And so, basically, maybe the most interesting thing about this workflow thing is that you can actually use this information, because a workflow is in its essence is a dependency graph. So you know exactly when a function, after which function it will be called. So there's a lot of possible, but we implement a very simple way to prewarm with Fission workflows. And the idea here is that when one function starts, you prewarm everything on the horizon. And what's the horizon? Horizon is basically, here in this case, all the functions that are right up in line after the first function that has started. So in this case, the next three will be prewarmed. And then once the first finishes, then all the ones that are prewarmed can immediately start and benefit from this prewarming. And this process goes on until the entire workflow is completed. And in general, you can imagine that if you would have done this yourself, basically by calling functions from one function to the other, that would be much slower, because now you can prewarm everything in the sequence. So, and just to finish our model, we can add this small workflow component to this image. Of course, a workflow engine is much more complex than a single box here, but just for the sake of simplicity, it's a single box. And because the important thing here is that there's now a arrow from a workflow engine to the deployer, which means basically that the deployer is no longer solely dependent on the router for basically deploying functions. Now also something else can deploy the functions. So to summarize, we've seen here 4 techniques that are used to improve the performance of function and service platforms. We've seen that function resource reusing is used by basically all the function and service platforms to trade in performance isolation for better performance. We've seen that you can basically cut in half the deployment process by having these pools of generic runtimes. And we've seen that this prefetch optimization allows you to deal better with large functions across more geo-distributed settings. And finally, we've seen that you can try to avoid this entire cold start process entirely by using prewarming to predictively deploy your function instances ahead of time. And then we've also seen that every one of these optimizations is a trade-off between performance and cost. And also that raises an interesting distinction between the closed source serverless platforms and the open source serverless platforms. Because as of today, most closed source platforms don't actually give you the flexibility or the freedom to tweak these trade-offs yourselves to fit your use case. So you have to rely on them to actually have made the right decision, have made the right decision for your exact workload. And whereas in contrast with open source service platforms such as Fission, you have the full control and full flexibility to tweak these trade-offs to fit exactly the performance needs of your application, ensuring that you also pay the minimal cost. And that also brings me to what I think is very interesting about serverless, is that it's not just a model where you pay for the resources that you use, but you can also just pay for the performance that you need. Thank you very much. Okay.